Hi everyone, I hope you're doing well. Today our goal in this lesson, this example, is to take a thorough look at a machine learning application, and this is going to be a regression analysis with wine quality data with the ultimate goal of creating a predictive model to predict wine quality. And you'll see we're going to do this in two different ways, and then take a look at those two different approaches and make some conclusions about which approach might be better given the situation. So what we want to keep in mind here is that when we are conducting a machine learning analytics project, we usually have some kind of stakeholder, a business professional who might have an interest in our conclusions, and we'd like to be able to make recommendations and bring some insight to perhaps inform some kind of decision-making process. So the data that we're going to use today can be found either on the UCI Machine Learning repository or on Kaggle. It's in both places. So if you take a look at the UCI Machine Learning repository, you're going to find just a ton of different data sets, and you can see which ones are most popular. And then, look through, you can search based on a topic of interest. And if I look at this wine quality data set is pretty popular. The way to get to the data is to click on the heading, right? Wine quality data set, and then click on the data folder. And then you can see that the wine quality data sets are in here, and you can actually just read the data directly from the URL. So I'll show you how I put together a URL to read that data. Okay, so it's winequalityred.csv. If I click on the file, it's downloaded, but what I need to do here to create the full URL, right, is to highlight this name of the file that I want to use and tack that on to the end of the URL when I'm reading in the data. Okay, so that's a pretty cool option that we have, reading data directly from the URL, so we don't have to try to read an external file. So it can be helpful to avoid that. All right, a couple references and resources here. Scikit-learn. There's a scikit-learn cheat sheet, Pandas, and Seaborn. Those are a couple of the libraries that we'll use heavily throughout this project. So we'll begin by exploring the wine quality data set. Okay. Notice I'm importing Pandas, and I'm using the read CSV function, and I'm indicating the type of separator that's being used. So I had to take a look at the data to notice that the separator is actually a semicolon. And if you read really carefully about the data set, the description of the data set, you're able to find that information, but you have to be pretty detail oriented to make sure that that works for you. Okay, so everything works, and I'll tell you right now, I didn't have everything right the first time, right? I had to get the separator just right. I had to set header equal to 0 to make sure that the header values were assigned as the first row of the data frame. So you'll have to do a little trial and error to make sure you get all this right. And of course, you can always take a look at the read CSV documentation in the Pandas library. Okay. So here are the variables that we have, quite a few characteristics of wine, and ultimately the goal is to predict quality, and that quality is on a 10-point scale. So we have things like density, pH, alcohol, chlorides, sugar. So all of these values are expected to contribute in some way to the quality, and if they don't, then perhaps they should be eliminated from our model, right? We want to be able to come up with some model that figures out the relationships between each of these individual variables and the response variable, which is the quality. Okay. I'll notice at this point, we'll talk about it again later, but notice that the variables are measured on different scales. So that's going to prompt us to do something special at some point. All right, at this stage in the project, I would probably do describe for my data frame just to take a look at the statistical summaries for each one and get a sense of the means, the standard deviation, the 5-number summary. It can be useful to just take a look at this and refer to it. Notice we have the count, which tells us how many records we have in our data frame, and that's useful to know as well. Okay, so different means because the variables are measured on different scales, right? And then different measures of variability, all relative to the scales of each of the variables. Okay, another tool we can use when we're orienting ourselves to a data set is the info function. And what this gives us is some more information about the data types. Okay, so float, and a lot of times this happens when we're reading data from a file. We get float 64 and 64. I think that just has something to do with the bits, 64-bit. I'm not sure. I shouldn't say too much about that, but we can read this as float and int in the usual way. Okay, so here we can see then that all of the results, all of the predictor variables are float, which means they are continuous variables. And we can see what that means by looking at the data, right? Continuous variables means they're measured with, they theoretically could be measured with infinite precision. Somebody has made a decision about rounding, right? But in general, they're measured on a scale that has no incremental separations, unlike the quality variable, which is an integer, that's a discrete variable. That's measured on a 10-point scale, and there are no numbers, say, between 5 and 6. A number can only either be, it can only be one integer value, and there's a cutoff at 10. Okay, so that's called a discrete variable, and usually discrete variables are going to be measured with an int as an integer instead of a float. Okay, and that just tells us something about the nature of the data, and it informs us on what kind of model we're going to use. Okay, so you've seen a little bit about regression modeling, and you will know at this point that when we're building a linear regression model, either simple or multiple regression model, we require most of the time continuous predictors, although it's possible to use what are called dummy variables, which are just zeros or ones, to basically recode some kind of categorical variable. Okay, so that's a little bit of an orientation to the data. At this point, let's take a look at something called collinearity. So I'm introducing you to a statistical term here, and I'll say a little bit about this and why we do it in part as part of a project like this. What we care about when we're building a model is that we have independent predictor variables. Okay, so all these variables that we have in the data set, the acidity, volatile acidity, citric acidity, I keep referring to those as predictor variables because those are the variables I'm going to try to use to explain or predict the outcome variable, which is the quality, or that's the response variable. Okay, if these variables are related to one another, then we view that as a case where if we use both of those variables as predictors in our model, we're essentially inputting the same information into the model. And what that can do from a statistical perspective is it can exaggerate the performance or accuracy of the model. So without going into too much detail on that, you can research collinearity if you're really interested, but it's something we want to avoid. So at this stage, we usually look to see if there are correlations between the predictor variables, and oftentimes we will leave variables out if they're related to more than one of the other variables. That way we can be sure that we have unique predictor variables. Okay, so how can we do that? Well, there's a nice feature that's part of Pandas called core. So we can use df.core to take a look at all of the pairwise correlations among the predictor variables. And notice that, of course, we're going to have a group of ones across the horizontal. Remember that a correlation equal to 1 means that the variables are perfectly correlated, right? So in a sense, knowing x allows you to predict y exactly. That's what a perfect correlation means. Correlation can range between -1 and +1. Values of -1 also indicate a perfect correlation, but in the negative direction, meaning that as x increases, y decreases, and vice versa. So we're looking out for correlations among the predictor variables that are close to 1 or -1, and those might be cause for concern and reason for us to remove those variables from the model, from the collection of predictor variables. Okay, so that's a choice that you as a business analyst or statistical analyst would have to make. Okay, here's another way to accomplish the same thing but with a slightly nicer output. I would import, there's some specialized things that I'm importing here, some special kind of font, but I definitely need NumPy, Pandas, Seaborn, and Matplotlib, PyPlot as PLT. I might have some redundancy here because a lot of these libraries, like Pandas, is built on top of NumPy, so it includes all the functionality of NumPy. Seaborn is built on top of Matplotlib, so it includes the functionality of Matplotlib. So perhaps some redundancy here because I'm not using all these libraries, but that's okay. Okay, so this didn't render. Let me see why that is. Okay, so this didn't render at first, so all I did was add in this plt.show. That was kind of a stab in the dark, but that ended up working. So plot show is a way of making sure that your plot renders in the browser. Okay, sometimes because we are using this browser-based software of Jupyter Notebooks, we sometimes don't get our graphs rendering, so we might have to take an extra step to do that. Okay, so here is a really nice looking visual that shows us the correlations, and this is generally something you would do in the exploratory phase. All right, so I'm seeing that values that are close to this, dark green or dark red are going to be cause for concern. So aside from the diagonal, which is always going to be 1s, but I can see the fixed acidity seems to be negatively correlated with the pH. Chemistry people would understand why. So that one's dark green. Citric acid is negatively associated with volatile acidity. And then let's see, what's the red one? Red. Fixed acidity is associated with citric acid. Okay, so a lot of those acid variables are related to one another, so we have some redundant information in the model. So we might make a choice to remove perhaps fixed acidity or maybe more. Okay. Here's another way we can take a look at the patterns in the variables, and this is super useful. There's a lot packed into this graphic here. This is from Seaborn. It's a pair plot tool, and all it requires is a Pandas data frame, and that's the only argument I need to create this pair plot, and it's labeled for me and everything. This is why I really like Seaborn. Then I can see the distributions of the individual variables. I get histograms across the diagonal, and then outside of the diagonal, I see the scatter plots between the two pairwise variables. Okay, so fixed acidity, again, I'm seeing how that variable is related to, it looks like 3 of the other variables in the data set. Okay, right, so that's a very, very useful plot as part of your exploratory tasks. All right, based on this, I might want to examine some of the scatter plots more fully and plot those variables individually. So to do that, I would use the Seaborn scatter plot function, and I would select the variables that I want to use. I can notice that I can simply say x is equal to density, y is equal to alcohol, as long as I include the argument that says data is equal to the data frame, and then this function will read the data frame and read the variables directly from the data frame. So I can see that there is a pattern between density and alcohol. Okay, here's another one looking at density and fixed acidity. Okay, so density is related to both of those variables. So I'm discovering these patterns among the predictors. When I do discover these patterns, what I could do is drop them from the data frame. So just for this example, I'm only choosing to drop density, and then the reason I'm dropping quality is because I'm going to be creating a data frame that is only the predictor variables. I'm going to deal with that data frame separately from the response variable or output variable, target variable. There are a lot of different names for it, but the quality is going to be removed from this data frame of predictors that I'm going to call X. All right, so moving on to now we're moving into the early stages of building the model. Okay, so now that I have this data frame of only the predictors, I'm going to refer to that as X. So notice that quality is no longer there. Okay, I better run this because I'm probably going to reference it later. I didn't run the scatter plots, but that's okay. All right, and then I'm also going to define Y as the quality variable. Okay, and I'm using an additional function called unique here to take a look at the actual values that I have in the quality variable. Okay, so those are all integers, and the only values I have are 3, 4, 5, 6, 7, and 8. Okay. Okay, next step, which you've seen, can't remember if I ran that. I think I did. Next step, which you've seen in your scikit-learn course on DataCamp, is to import your linear regression, because that's the type of model we're going to fit, linear regression model. And then I'm also going to import the train test split module so that I can split the data. Okay, so now I have the libraries that I need. The next step here is to create a variable for the linear regression function. So I'm going to say LM is equal to the linear regression function. I'll reference that later. And then I am going to perform the split, and there are different ways to do this. I think this resembles the way you've seen it in your course. We set up the X train, X test, Y train, Y test, right? And the train variables are the ones used to build the model, and then the Y or the test values are the ones we use to try out the model to see how well it performs. Okay, so then we have train test split. We specify our X data, our Y data, and then we also specify what is our test size. So that's telling what percent or what proportion of the data should be left out of the model fitting process. And then that data will be reserved for testing the model. We also often specify a random state, just so when we run this, as we're building this program, if we run it over and over again, we'll get the same results. Okay, so let's run that. Let's split the data. And then let's run the fit. So this is where we actually run the linear regression model and build that model based on only the training data, X train and Y train. Okay, so now we have a linear model that's been built, and then we can use it to create some predictions. So those predictions are built by simply plugging in now all of the values that were left out in the testing data. So we're trying to predict wine quality based on all of the other variables in that 30% of the data that was left out for testing. Okay, now our next step is to evaluate the model to see how good, how well it performs. And you saw in your lessons that there are a variety of metrics that can be used to evaluate the model. One of them is mean squared error, which is the average of the squared differences between the predictions that were based on the model and the actual observation. So you can think of it as this average squared prediction error. The root mean squared error is the square root of that, which is more intuitive. You can interpret it as the average prediction error. How far on average the predicted wine quality was away from the observed wine quality. Okay, so those can be interpreted in the context of the problem, in the context of the data, and they really have to be interpreted and understood in the context of the variables that you're measuring. It's nice to have a metric that is independent of the scale of the data that you're working with, and that's where R squared is useful. Okay, so that's found using the score function, which is built into this LM, this linear regression module. Okay, so I find the R squared value, and I'm doing this for both the training data and the testing data, and this is a common thing for us to do. So for the training data, I get an R squared value of 33%. It's usually interpreted as a percentage. And then the validation score is 41%, which is a little funny because usually oftentimes the validation score is lower than the training score. But there's a lot of random variation here that is unexplained. So you may remember R squared is also called the coefficient of determination. And it's interpreted as the percent of variation that is explained by the model. So in this context, we might say something like, so for the test data, 33% of the variation in wine quality is explained by the regression model. And whoops, I have this backwards, sorry about that. So this is train, and then for tests, also called validation data sometimes, I'm just going to say the same thing, but it's going to be 42. 40% of the variation in wine quality is explained by the regression model. And that basically means that the other percent of variation is unexplained. So it's either due to other factors or just random variation, things we have not been able to account for with the predictor variables that we've been able to measure. Okay, so that's how we interpret R-squared. A good R-squared is going to be close to 100%. A bad R-squared is going to be closer to 0%, and then somewhere in the middle is maybe okay, but these R-squared values are not very good. It's telling us there's a lot of remaining unexplained variation in the data that our model has not been able to account for. All right, so we switch gears at this point. And this is what a sophisticated data analyst would do. They might say, well, I'm not getting a good performance based on predicting wine quality on this 10-point scale. So what if I just group the values into, say, low, average, or high? And that's what this little program is doing here. This program is setting up a new variable called reviews, and it's taking in the quality measurements and saying, okay, well, if a quality is between 1 and 3, then let's give that value a 1. If a quality is between 4 and 7, let's give it a 2. If it's between 8 and 10, let's give it a 3. I saw there was nothing higher than 8, so that's only going to include 8s. We create a new column called reviews because perhaps we just care about these 3 categories. It's much easier to predict fewer categories than it is to predict multiple values like we were trying to do with predicting precise wine quality. Okay, so that's the idea here. Maybe we can get better performance if we can look at more of a granular output variable. So I assign this, first I look at the columns to make sure that I have been able to add the reviews to the data frame. So now now the data frame contains a reviews column. Okay, so then I look at the unique values and I see I have 1s, 2s, and 3s. So basically I'm just checking that my results have worked. Another thing I can do is use a counter tool, and that's from a collections library. So from collections I'm going to import the counter, and it just gives me a really quick way to count the frequency of observations in a particular column and see how many times is there a 2, how many times is there a 3, and then how many times is there a 1. Notice how common the 2 is, right? So there are a lot of average rated wines. Okay, so that works. Here I am now creating the new collection of predictor variables as the X, storing it as a variable in Python. Python variable is different from an actual variable in the sense that I've been talking about them. But I'm creating a new data frame of predictor variables, removing the density as I did before, and then also removing quality and reviews because I now have kind of 2 versions of the output variable, and I'm going to ignore quality for the rest of the program. Okay, so I run this next step to create the data frame of output variables, just the reviews. Okay. So the next few steps are optional, and I included them just because you may come across these techniques and they're fairly ubiquitous in machine learning and in statistical analysis. When the variables are measured on different scales, it's kind of common to standardize the values to even out those contributions that each variable makes to the model, and that's what I was referencing before when I was looking at how the variables were measured in somewhat different ways. So scaling the variables makes everything into z-scores, which is z-score is just a measure of deviation from the mean of a distribution in terms of standard deviations. So basically values that are close to 0 mean that the value is closer to the mean. Values that are closer to, say, 2 or even 3 indicate values that are farther from the mean, either negative or positive. So that's a way of just evening out the impact of each variable. All right, the next step is going to be optional. I'm going to just skip over it. This is a technique that automates the process of selecting those independent predictor variables. So rather than relying upon our own judgment, where we look at the correlations between predictor variables, we can use a process called principal components to automate that for us and tell us which variables we should use in the model. That's more sophisticated, and we'll just skip through it. We'll move on to the train test split, partition the data. Okay, gotta go back and fix something. Okay, no problem. I had to fix a reference here. I'm not going to use the results of the principal components. Instead, just going to use the data frame of predictor variables that I created. And now I'm going to use a logistic regression approach. Okay, so logistic regression is very similar to multiple regression, but differs only in the nature of the target variable, the thing we're trying to predict. And notice that I am using all the same data, except the only difference is that I now have what I would consider a categorical response variable or target variable, because I now have wine quality in groups of low, average, and high. So when that's the case, a logistic regression model is appropriate. Okay, so instead of linear regression, I import logistic regression from scikit-learn, and I import something called the confusion matrix and the accuracy score. So two tools that will allow me to evaluate the model. Okay, so I run that. I'm doing a whole bunch in here, right? I'm doing the partition and also the logistic regression fit. So I should have a comment here. A logistic regression usually has only two output variables. But we can predict three or more. We could predict two or more output values, I should say, right? Because I have a 1, a 2, and a 3. So this is okay. I'm just pointing that out because usually you'll just see one output variable, like a yes or a no kind of thing. All right, so that works. And then finally, let's evaluate the performance with something called the confusion matrix and the accuracy score. The confusion matrix, you probably saw, is this table that basically shows correct and incorrect predictions. So if I look across the diagonal, I can see that one, so what was this? One of the wines that had low quality was predicted to have low quality. 3 of the wines that have low quality were predicted to have average wine quality, and then 0 with low quality were predicted to have high quality. Okay, now I'm looking at the middle value here, 468. That's telling me that there were 468 wines that actually have a low average wine quality and were predicted by the model to have an average wine quality. So the actual results are in the rows of the matrix, and then the predicted results are across the columns of the matrix. So just to make this really sink in, there was one wine that had average wine quality but was predicted to have high wine quality. there's sort of a problem here. Our model didn't do that great predicting high wine quality, right? All of the actual high wine qualities were predicted to have average wine quality. Okay, so, but because our model did so well predicting the averages, we end up with an accuracy score of 97.7%. Okay, so our model does pretty well separating the wine qualities based on that collection of predictor variables. Okay, so overall, what does this example teach us? It shows us that we can use our domain knowledge of a problem and make some decisions about the variables and manipulate the variables in such a way to improve model performance. So I hope that this example is a helpful way to put a lot of the techniques together that you've been learning over the last couple of weeks. And I'd be happy to discuss any of it with you further.